Hello, my name is Roberto Norris, and today I'll be discussing a tale of two motors for my electromechanical project. And excuse me, I do have two screens to keep track with the PowerPoint, but also keep track with the notes and everything. Now, the two motors that I have chosen today to present would be the reed switch motor with the transistor and the motor on Hall effect switch. Now, to briefly discuss the design and the armature of each one. Essentially, we have two brushless DC motors, as there's no brushes connected to each means, and it's simply just an open, you could say maybe an open casing, as you want to call it, for each of the motors. Now, the reed switch motor with the transit. Now, these are both built around pretty much the same, except the reed switch motor with the transistor is built more with the preservation of a reed switch in mind, as the reed switch creates a spark every time the inside of it is magnetized. That spark can cause problems over time, obviously, and with just a heavy use DC motor such as this one, as the RPM greatly increases over time and can become very fast by its peak. That can actually cause a lot of problems for the reed switch when trying to generate and trying to constantly connect. So with that, hopefully it's easier to put in the capacitor with the heat sink also, but also with the to kind of curb essentially the flow of current that goes through the system, so that the reed switch doesn't necessarily receive too much power that it could, overload it. Now, when we have the motor on Hall effect switch, we go over here, we essentially eliminate more of the problem that the reed switch presented. And so with that, then the reed switch, instead of the reed switch, instead of the reed switch and its connections, it is then used and converted by a sensor which detects the magnets present instead of being magnetized together to create that kind of a spark and that signal to send versus. So now, since it is an electric signal sent to the base, which is what the reed switch is also connected to, that allows for easier openings of the collector and emitter to allow more current to flow in the system. Now, for the motor design, I have placed the diagram for the reed switch at the top and the diagram for the Hall effect at the bottom. Simply put, these are both pretty much the same designs as you see, even with the connections onto the transistors, the transistors, the coils, and even the way the electromagnetics are placed within the middle. The electromagnetics are relying on similar effects to generate voltage within each motor, and as they are both actually considered brushless motors, as I've said earlier, they're only controlled through electrical signals generated by the windings, which is just the current creating the magnetic field that it then pushes the magnet to begin its rotation and to interact with the reed switch, as it is also carried by the inertia from each general push. Now, the reed switch only needs the capacitor, as I said, to the power supply through the reed switch itself. The magnets are set on the stator to open the base of the transistors as they interact with the sensor throughout the rotations to allow greater currents to flow. So for this case, if you were to remove the stator, you are removing the main component of each motor, as the stator is the one that holds the magnets that they need to be used for these motors. Now, both the reed switch and the Hall effect hold stators with no housing, and no stator means no means to generate electric charge for its system, and no electric charge, nothing flows, nothing can move. Now, the DC motor. To just briefly touch on DC and AC motors, DC motors can reverse shaft direction by switching polarity, as is powered by the direct current, which means powered by a single supply itself. Changing flow direction does not eliminate the flow of the current source. It is simply put, so just reversing it would just be to reverse the polarities of the system itself. But the power is still essentially sent the same way. But since that flow is redirected, then the motor would change. Then the DC motor would change, versus an AC motor, which is not easily able to change directions due to alternating power, as it is alternating consistently more in a wave from positive to negative. So to reverse directions on that one, that would actually need another means to, you would need to mess more with the field that would be generated from an AC motor. So now to look at ours, now look at our shaft rotation and everything. The polarity of the two brushless DC motors, since it is, and I'll discuss this a bit later in the presentation, since it is DC power being converted into AC power, actually, it's not easy to just simply just reverse the direction on the stator of the motor, because that AC power is being converted consistently, and so it's interacting more with the magnets in the system more in a kind of square rectangular way versus a straight consistent power. Now the torque of the, what is it? And then, oh, well, while fully active torque does not have small shifts, but it does have small shifts, but it's not outright change in the power supply, and the current is steady, so it increases, then it reaches a peak to match the system power from the supply. The torque, essentially, your RPM pretty much stays constant when it reaches its peak, its max level. It doesn't ever change. There are slight shifts, however, so there are, you could say the torque maybe minusculely is changing for the system, but that's more kind of negligible because it's more within the hundredths, to the decimal range. Is not anything that's going to be, outright significant, like a strong jump from, like, say 4 to 6 within this voltage, which then actually could more change its torque and actually would be more important. But it is not possible to reverse rotation, reverse out, and Hall switch due to the converted AC power, as I've stated earlier. Now to go into the next part, which is actually destruction testing. And so simply put, destruction testing, it just would be to just put them in, to just push them to their respective limits and be burned out to failure. So for these type of switches, it's very easy, as there is no real self-start and self-stop. So for these, they are not ever stopped on their own. You would have to unplug essentially the power source itself to stop them, or maybe have some sort of load and friction that could maybe stop it, but that is to be discussed later on also. Now, both can actually, so for destruction to make it simple, both can use the same method of destruction, as they use the same single supply power from the battery pack. So a preferred method would actually be to just use that same battery pack connections, not necessarily the same battery pack, but just like general positive and negative connections with a larger controllable power supply that you could adjust, or even just work in stages with different voltages to continuously test it until it reaches max level. Now with the reed switch, this would be a lot easier, as you would be just testing till the reed switch would actually go out, as the stator and the coil would just keep going. It doesn't necessarily burn out. It would just become too much for the armature maybe to handle. But the reed switch was absolutely easy to burn out through the sparks. The sensor, the Hall effect, would be a bit harder, since that's more electrical, but it would still be also possible through the same means to do that same route. You would just have to push it to respective limits as well. Now, both motors operate under manual functionality, only start stop when the power supply is attached and detached, as I mentioned earlier. However, while they are currently not designed for automated function, it is possible to have it self-start and self-stop. Now, the self-starting is a lot easier to say than the self-stop, because since it already is receiving AC power, it is more as a brushless DC motor. If you can connect that AC power and be able to just use the entire system more with the AC power, even though it is converted, then you could possibly have it work with self-starting, as it would be receiving a signal, and you could have that means act as a signal over time, a frequency that you would be measuring essentially, that would be measured, and you could use that to try to tell as soon as you receive the signal. Else, it would just be not necessarily actually possible to even self-start that. But the motors already work under AC power and is converted, not necessarily received. So again, self-starting would be a bit hard and not necessarily even close to ideal for the system. Now, self-stop could be simple, just add a timer or an automated switch. Even though the transistor kind of acts as an automated switch, that's more just for current flow. That doesn't stop the system itself. You would need something to actually disconnect the power in general for this to stop that. Now, converting a motor to a generator would not be necessarily the hardest thing, but it would be a bit of work for the system. Now, but first loading up the motor to do that is simple as anything that draws power from an output. So you could couple the rotor to a pulley-based system, would be ideal for the small motor, because with our two that we're looking at, the reed switch and the Hall effect, both of these, while they can generate mass RPM, they can generate absolutely crazy speeds. Now, these would take a hit, and these are smaller systems that they have to generate its own power to help run it's just this other system that is connected to entirely. So in that case, you would start incurring losses, such as like friction loss within the system, which become a bit harder to do. And the RPM would absolutely take a hit after having load added onto the system. So you would have to add on to it just to make it work. But it would actually be easier to load this up. Now, to convert it into an actual generator, it has to be able to convert that same work that you are loading it up with. The load could be, even added on with maybe a couple like resistors or something like that to generate the actual mechanical work. For that, you would have to attach that to maybe a bigger system, which then would be a turbine, a propeller, et cetera, to generate voltage for this system. Now, by the generated voltage that it would create would be decently lower than supply, would be still pretty healthy based on how much the RPM and the speeds that it can generate for the system. So it does have enough horsepower to at least get some wattage going, but it would not be anything too crazy or too outstanding for it to work. Something decent necessarily. And then if you look at how fast that this stuff goes, the speed could actually be controlled through the power supply. So the DC power essentially would mean no fluctuations, and its constantly unchanging voltage storage keeps the velocity constant as it just essentially goes and steadily reaches a peak and then maxes out before, instead of it kind of fluctuate. Now, when it does get to that peak, it does still fluctuate, but still. Now, possible alternatives is you could mess more with the AC power instead, as I was discussing earlier, by having it fully connected to a full range of AC power and just completely taking out the DC in general. It's a lot easier to connect or control the speed through the post frequencies. Or you could even use a potentiometer to the power supply to control the speed, as you would be controlling the voltage directly instead of even having to just send signals through to get it to adjust on its own. Now, the RP, finally, just talk about RPM. The RPM can be measured through the frequency, specifically in regards by rotation, by measuring the number of cycles in the motor, by the motors, as I was discussing earlier. So what essentially you're doing is you have to measure those cycles as its own frequency per minute, but you have to still realize that this is more kind of like a general speed. But the measurement tool that you can use, like a sensor, would count this as a frequency, like this would be in hertz, because it is treated as such through the cycles, because each rotation can be treated as a cycle, just like how you would treat a regular section of a wave as frequency. It's being converted. And then for the final one. And so now then we finally look at single phase and special purpose motors. So for single phase motors, these are commonly used for everyday households and businesses, and most aren't really actually equipped for three-phase power. Most actually only need single phase power for what they would do. because three-phase powers is when you start looking at more like industrial means and full ratings and everything for these bigger systems. So for universal, so when we look at single phase motors, we have two mainly. Universal motors, which are made for DC and AC power, as the name suggests, but these can only really be used for lightweight, high torque applications, like such as drills, vacuum cleaners, and other small motors that are required. But because they can be used for DC and AC power, this does make them very viable, obviously, in common use, because it can just be used anywhere for any time with no problem. Versus now, if we look at the induction motor, an induction motor is a very specialized single phase motor, as it is only capable of use with special designs. It's not run through as a rotating magnetic field. What it actually does is it pulses in a singular position. So that has to be used in conjunction with a different type of circuit design, as you can't just attach that and it's not inducing any voltage or current in a regular means. You have to measure that in a different way. Now, special purpose motors are just motors where we would be looking at simple, straightforward kind of means, where they just have their own usage. They don't necessarily have any other real uses on it, like reluctance or hysteresis motors in various select systems. Reluctance motors are very specialized because they use reluctance torque, for example, and that isn't an easy torque to necessarily control, even measure, and handle. You would have to get a special means to be able to convert that within its system. So, and then to finally go into what we've been talking about, this presentation, the brushless DC motors are included as a means to increase the lifespan of very heavy use DC motors. Like when we're talking about the reed switch, and you see how that constantly creates more of a spark and a easier wear on the reed switch, versus using, say, for instance, the Hall effect IC on that. That is what we want to try to eliminate. But with the brushless DC motors, you're also eliminating the other incurred losses from the brushed system, as it interacts more with either brakes or this armature goes with the brushes. That's easier wear on the system itself. But when you take away these components, and you also take away any possible losses that could be incurred from the brushes by being, grinded on those pieces together within the shaft and everything, then it's a lot easier to see its true peak in what it can achieve under DC power, versus just trying to use that DC power and end up wearing it out over time. That is my presentation. That is the info for the reed switch and the Hall effect IC. I thank you for your time, and please be easy.